We have been seeing that a standing wave can be produced by overlapping two progressive waves that are traveling in opposite direction. And through the principle of superposition of wave, we are able to determine the equation for standing wave and the wave pattern for a standing wave. So now we are going to study three different situations in which we can produce a standing wave. And we are going to focus on the fundamental tone, which is the simplest possible wave pattern for a standing wave. So the three situations that we are going to study are stretch string, open pipe, and closed pipe. So let's focus on the first one, which is on stretch string. So a stretch string situation can be found on a musical instrument like a guitar. So you can see that the guitar have the two ends of a string being fixed on both sides of the guitar. So we know that the string is fixed at both ends. So if we are having a string of length L, we know that this simplified representation here have these two ends of the string being fixed. So being fixed means that these two ends here, there will be no displacement undergo by the particles of the string. The string cannot oscillate, the string cannot move up or down for both ends of the string over here. And since we know that the displacement is always zero at both ends of the stretch string over here, we know that these two ends here will be a note. Okay, because notes are places where the displacement is always zero. So next we know that notes and antinodes must alternate. You cannot have two notes next to each other, you cannot have two antinodes next to each other. So know that in between these two notes here, there must be an antinode so that the notes and the antinodes alternate. So therefore, we will introduce an antinode in the middle here so that the note and the note over here doesn't lie next to each other. So now once we have filled in the gap already, we know that the shape that will be produced by this fundamental tone here will have displacement equals to 0 at both ends of a string, which is the note, and the displacement will be maximum at the antinode. So we know that the pattern or the wave profile of a fundamental tone will be something like this. You will see 0 displacement still remain at its equilibrium position at the note, but at the antinode you can see that the displacement is maximum, or you can say that it has maximum amplitude at the antinode. So you know that this is a standing wave, so the wave will be moving like this with time. So you know that there's a version where the standing wave is on the upper side of the above the equilibrium position of the string, and there will be at certain moment the curve will be below the equilibrium position of the string. So you draw both versions of the oscillation of the standing wave in the simplified diagram over here. So this is how we represent a fundamental tone for a stretched string. Next, you know that from a previous video, we've mentioned that the distance between two successive notes, is always equal to the half of a wavelength. So you know that this distance here will be lambda over 2. So you know that this is also the length of the string. This is half of the wavelength. So you can equal these two things together and say that the length of this stretch string over here is equals to the wavelength of the fundamental tone divided by 2. Okay, so this is a statement that we will make for the fundamental tone of a stretch string. Or in other words, you can say that the wavelength of the fundamental tone will be equals to twice the length of the string. You can think of it like this. If you double the wave pattern that you see here, then it will complete a wavelength. Okay, so this one is up. If we double this pattern on the other side of the string, you see that it complete a sigmoid, it complete an S shape. So this will be one complete wave cycle. So the wavelength of a fundamental tone is equivalent to 2 times the length of the string. Okay, so this is the fundamental tone for a stretched string. Let's move on to the fundamental tone of an open pipe. So when we talk about an open pipe, we are saying that the pipe is open at both ends. So you can imagine like a water pipe, but both ends are open. Okay, so a musical instrument that has its pipe open at both ends will be a flute. So this is a flute. You blow at this hole over here, and this hole here is open as well. When you are blowing on a flute, you don't cover the whole hole here. You don't cover it with your mouth. You're just blowing through the hole over here. Therefore, you are not closing it. So this is the open end of the flute. This is the another open end of the flute. Okay. Then by pressing the button of the flute over here, you change the length of the pipe. If you close all the hole, then the far end of the open pipe will be here. Okay, but if you open, let's say you open this hole, then you are shortening the length of the pipe, allowing an open end over here. Okay, so but one of the open end is always here, just that the another open end depends on where you press on your button of the flute over here. Okay, so the air particles near both ends are able to oscillate freely. The idea is that this: if you have a pipe which has a length of L, then the open pipe says that this end of the pipe and this end of the pipe here are open. There's nothing blocking it. So if you have particles on both ends of the pipe over here, you should expect the particles being able to oscillate freely. You don't have something to block the particles from oscillating. So if you expect the particles at both ends to be able to oscillate freely, then you know that the displacement is not locked to 0. If it's a stretch string case, you know that the particle at pin over here already, you can't make it oscillate. So here there must be a note. But for here, since this is an open end, you know that the particles are free to oscillate. So therefore, you should expect both ends over here to be an antinote. Okay, and now you know that antinodes and nodes must always alternate. You cannot have two antinodes side by side. Therefore, you know what you need to put in the middle here will be a node. Okay, and once you have done that already, you know that the distance between two successive antinodes will be equals to lambda over 2. But before that, we look at the pattern first. Well, node means by the displacement is always equals to 0. So you can see here, if you take this dotted line here as equilibrium position, then the y will be equals to 0 at the node. For the antinode over here, you expect the displacement to be always maximum. So therefore, if you compare the displacement at the antinode compared to any other places, you see that the displacement at the antinode, it's always the maximum. There's no other place that has greater displacement than the antinode. And you also know that antinode is the place where you have maximum amplitude. And this is the pattern. Okay, this is the this is the pattern when you have your maximum and when you have your and when all the particles reach their respective amplitude. Okay, you see that the maximum amplitude occurs at both the antinode over here. Okay, so I have this blue line here representing what you draw for displacement against position. So displacement, it's y, then x is position. So this blue line will be what you draw for an open pipe. But what is this blue sigmoid line here representing is actually representing the displacement of the air particles, right? So if I represent each air particles here as lines over here, if you can take each line over here as rows or columns of air particles, then if you have a great displacement, let's say this is great displacement in negative direction, then you see the particles, it's displaced very much to the left. Okay, let's see for one moment. Negative maximum displacement, then you see this line is displaced very much to the left. Positive maximum displacement, you see this line is displaced to the right. Okay, at the node, you see that this is where 0 is, then you see this line here never move because there is no displacement. Let's look at this point over here. Maximum positive displacement, then you see the line move maximum to the right. Maximum negative displacement, the line move maximum to the left. Okay, so that's the idea what you should be imagining. You should be imagining whether the particles is being displaced to the left or to the right. If it reach maximum, that means the displacement is maximum. If it's a positive displacement, the line is up. If it's a negative displacement, then the line is below the equilibrium. Okay, so that's how you imagine what does the pattern shown, what is the pattern that you draw here means. Okay, so the distance between two successive antinodes is always lambda over 2. So from here, you know it will be a similar situation to a stretched string. you know that the length of the open pipe will be equals to the wavelength of the fundamental tone divided by 2. Or in other words, you know that the wavelength of the fundamental tone is equals to twice the length of the open pipe. So this is what you can know about a fundamental tone of an open pipe. Let's move on to a closed pipe. So a closed pipe is not a pipe that is closed at both ends. When we say a closed pipe, what we are saying is it's a pipe that is closed at one end. So one end still remains open while the another end is being closed. So a popular or a common instrument that is a closed pipe, it's a clarinet. So this is a clarinet. You blow from the mouthpiece over here, then yeah, you hear sound, but due to this is a musical instrument, you produce sound. Okay, so this will represent the closed end, then this will represent the open end. Because when you are blowing on a clarinet, you are using your mouth to close the whole mouthpiece over here. It's a very narrow opening, and your mouth will be closing the whole opening when you are blowing into a clarinet. So if you are closing this end over here, then this will be a closed end. Whereas this end over here, the bell, we call it the bell, this bell here is open, so air can flow. So over here, it should be an open end. Okay, so the air particles near the open end are able to oscillate freely. So the particles over here are able to oscillate freely, while the air particles near the closed end are not able to oscillate freely. So you should expect the particles over here to be fixed in position. No displacement for the particles that are at the closed end. So a simplified diagram of a closed pipe will be something like this. You draw one end to be open, whereas you draw another end to be closed. In this case, this wall over here represents that it's closed. You know that this end over here, the particles are able to oscillate freely. So you should expect here to be an antinote. Whereas for here, the air particles here are blocked by the wall over here. So you should expect no oscillation to happen for the air particles near the wall over here. So therefore, you should think of it as similar to like the fixed end of a string. So you can call this position here to be the note for the standing wave. Now you know that here must be a note, here must be an antinote. So you can try to draw the wave profile of the standing wave right now. You know that at the note, the displacement is always equal to 0, so your line should be at the equilibrium position at the note. For the antinote, you should expect the displacement to be always maximum, and in other words, you can also say that at the antinote, there's maximum amplitude. So when you draw your line, you should expect the line to hit the maximum at the antinote, whereas at the note, it is always 0. Okay, again, you can see that at the note, the air particles here, you can see it barely move. Okay, the note is right on the wall actually, so it never move at the wall over here. The air particles at the wall never really move, but at this point over here, you can see now it's maximum displacement to the left, now it's maximum displacement to the right, and now it's maximum displacement to the left. Okay, so you can see it's a repeated rarefaction, then a compression. So this is compression, all the particles squeeze together. This is rarefaction, all the particles get far apart from each other. So this is a situation for the fundamental tone in a closed pipe. Okay, now you can't see any two successive note, or you cannot see any two successive antinote in this diagram over here. So therefore, you cannot label lambda over 2 so easily in this diagram. But you know that the distance between the note and an antinote should be half of the half of wavelength. Okay, so if you are finding a distance between the note and the antinote, it should be half of lambda over 2, right? So half of lambda over 2 is lambda over 4. Therefore, you know that the length of the closed pipe over here should be equals to the 1/4 of the wavelength. And if you shift it around this equation, you know that the wavelength of the fundamental tone produced in a closed pipe should be equals to 4 times the length of the closed pipe. So you can extend this pattern here. If you extend it, you need to extend it 4 times. So let me draw it. 1 time, 2 time, 3 time, 4 time. So by extending the line for 4 times, only you are able to get the profile of a complete wave cycle. Therefore, we say that the wavelength of the fundamental tone is 4 times the length of the closed pipe. Remember, the L here represents the length of the physical thing, which is the length of the stretched string, the length of the open pipe, the length of the closed pipe. Whereas the wavelength over here is representing the distance for one complete wavelength. So that is representing the wave. The L is representing the physical thing. The lambda is representing the standing wave. Okay, so that will be the fundamental tone for closed pipe. So in the next video, we are going to study what will happen if we try to make a standing wave with a higher frequency. How do we make a standing wave with higher harmonics?